A very good morning to all of you. Thank you, Nimishka. So, in today's instructions, we have our first experiments on acoustics, and we are going to talk about spread of sound energy. Remember, we have already discussed this topic in our theory classes. So, we are going to extend further that as the practical work. We are going to discuss again about the free field and constrained fields. So we all have discussed that sound is a wave, and if you have a point source of sound, now just imagine how would you make a point source of sound. But before we talk more about it, if you have a point source of sound and if you have an isotropic surrounding, in that case your sound will spread in all possible directions and on a spherical wavefront. So the same sound energy per unit time will subsequently spread out on larger and larger surface area. Intensity is sound energy per unit time per unit area. So eventually it's power upon area. So intensity would be reducing as proportional to 1 over r square for a free field. So free field isotropic medium point source. Intensity would be inversely proportional to r square. So it's a very straightforward assumptions. I mean, there's nothing new here. You have done this thing for light as well. You have done this thing for electric field as well. So you have done this at many places. However, in real life, most of our sound sources are not exactly point sources. A point source of sound is one which emits in all possible directions without any reflections, without any absorption by the surrounding surface. But in practice, you will always have some reflection and some absorption. So let us assume that you have some type of hard surface on which the source of sound is placed, which is most logical to assume because you might have your source on a table. Say if you're listening music by a phone and you keep the phone on a table, on a tile, then in all those cases the reflections will happen from the hard surface and the shape of the wavefront will not be spherical but hemispherical. Assuming that a hard surface will reflect most of the sound, the all the sound energy is now constrained only in the half of the sphere and not the full sphere. Then of course your rate of drop of intensity with distance will change. It will reduce mostly. Similarly, if you have absorbing surface, if you have soft surfaces at the bottom, then you might have some absorbing surface. For example, if you keep the source of sound near a carpet, near a curtain, then all these surfaces are going to absorb certain amount of sound and the sound travel is going to be inhibited. So again in this case your intensity variation will r is no longer 1 over r square. So in today's experiment we want to find out that in our experience in our life when we perform an experiment how does I changes with r. So I will take a very general assumption that I is proportional to r power n. So remember, if it is free field, if it is point source isotropic medium, then what will be the value of n? Can anyone tell me? we have just discussed. You can guess easily from our discussion earlier. So if it's a free field, if it's a purely isotropic medium, then in that case, you know that n will be minus 2 because I is inversely proportional to 1 over r square. So that is for a free field. But as I argued, for a real life, you may not get 1 over r square, but you will get something else as n value. So we need to find out that. Now, when I say isotropic means I'm assuming that we are finding out the passage of sound intensity in air. That is what I'm assuming. But suppose at your home there is a wall and you are exploring the sound passage to the other side of the wall. Then from the source towards the wall, the medium density has changed, and therefore sound travel will not be in the isotropic medium. So when I say isotropic, I'm meaning that we are looking in air. That's right, Gamer and Nimishka. Thank you for answering. So in practice, n will not be 2, but it will be something else. And we have to find out what is n in our setup. So let me present a simple mathematical algorithm. Here I is intensity of sound and r is the distance from the source. I can multiply everything by a constant k1. So I is equal to k1 times r power n. K1 is a constant of proportionality. You all know from the classroom discussion that what could be K1. If you have any doubts, you can go back and check those recordings of the lectures. Most of our mobile phone which we are going to use to perform this experiment, the apps will give your answers or your readings in decibel. So I need to convert this into a decibel scale. So I by I0, I divide by I0, where I0, remember, is my um, constant, the minimum intensity, 10 power minus 12 watt per meter square. That if I divide on both sides, then you know that even I0 is a constant, so K1 by I0 will give you a new constant. And then I can take a log of both sides. So log to the base 10, I take both sides. So once I take the log, this is a product of the two terms. So when you take log, it will turn into addition. So the log 10 log k1 by I0 plus log r power n. This is how it will get converted. And I can multiply by 10 throughout. So 10 log I by I0 will give you 10 log k1 by I0 plus n will come down and you are multiplying by 10, so it will become 10n log r to the base 10. So this becomes my equation. Now if you look at this equation, then it is intensity in decibel, and this is what your recording device will give. Any sound intensity meter app on your phone will give you this kind of reading. So this is already available to you. R can be measured. So I'm in a position to determine N. How do I determine? Look at it. If I compare, okay, let me just rewrite this equation into this form. So as I said, this is your reading in dB, and we have already learnt in our theory class that it is called sound intensity level. When I represent the sound intensity in decibel, then it is called sound intensity level. This is in dB. So this is my left hand side. This all thing is a constant. Remember, K1 is a constant, I0 constant, log of a constant ratio. into 10 will give you some constant. I would call it as K2, and I will take all these things here. Now if I compare this with the equation of a straight line, then if I take this as my y parameter and log r as my x parameter, remember log r is the distance, the log r is my x parameter, then 10n will be my slope and k2 is my y-intercept. That means my graph should look like this. If I plot sound intensity level here and log r to the base 10 over here, then this is this intercept is k2 and the slope is 10 times n. Now if I know the slope as 10 times n, then I can find out n as slope divided by 10. And that's how I will come to know my n, and that's how I would realize how the sound intensity changes with distance. Yeah, so n is slope divided by 10. So how do we perform this experiment? So again, choose a quiet place to do this experiment. Now you are at home. So figure out a place, a corner, a time. You can do it early morning. You can do it little in the night if it's noisy in the daytime, or in the afternoon when everyone is sleeping. So figure out a quiet place and time to do the experiment. Remember, it's a sound experiment. So any surrounding sound, background noise will affect your reading. Use one mobile phone as a source of sound. For this, you would need two mobile phones. So you use your and use some friends, parents, siblings, etc. So, so, so use that, and also you can use your laptop as a source of sound if its speaker is working. You can use any app like Audacity or any other to generate a desired frequency. So use one phone or laptop as a source of sound. There are lots of tone generator apps available. Download a suitable tone generator app. Tone generator itself is the name of an app, so you can download that or any other. I'm not recommending any particular one. Use work at 500 hertz. From my experience, I have noticed that at 500 hertz, up to 500 hertz, the sound intensity from your phone, laptop is fairly loud. If you go at a higher frequency, the output drops. If you are using a speaker, a Bluetooth speaker, or a normal speaker connected to your phone, you can do that. Just see to it that don't keep the sound very loud. Okay, if you keep the sound very loud, your variation in the distance has to be much, so that you have to use by trial and error. So subsequent discussions, if anybody wants to do that after this class, after this online instructions, we can talk about it in our discussions. Use another phone as a sound detector. Again, you can use a laptop or whatever as a sound detector, but you would in general need two devices. So you can uh, borrow it from your parents, friends, siblings, neighbors, as I suggested. Just request them and people will help us. You can use an app like for sound recording. Again, there are lots of decibel meter apps. They are available. I particularly liked one app which is called Arduino Science Journal. So you all can try out this app. I'm not promoting it, but this app offers a lot many sensors at one place with a good recording facility, etc. It is from the Google, I guess. You can store your data online, share it, etc. etc. So use that app, or you can use any other app of your convenience. Keep the source and detector on a hard surface. So to begin with, as I said, what kind of surface you choose will affect the results. In fact, what kind of room you are doing, even that will affect the results. So it's a small room, then again the reflections from the wall will affect your results. So basically, if you can perform this maybe on outside balcony or something, where or close to a window, where the window is open and sound intensity reflections are reduced. If you can do it outside your home, like in your compound, it would still be better, or on a terrace. So I leave that for you people. If anyone wants to discuss that point, please, we can talk about it after the instructions are over. So here is how the Arduino Science Journal looks like. Uh, I will talk about it in a while. Keep the detector at a distance of 5 centimeter, 10 centimeter, 15 centimeter, up to, not unto, up to 40 centimeter from the source. So you increase, and remember these figures I'm giving you for the basis of experiment performed on my own phone. If your phone's sound output vary, you might as well have to change these distances. You have to look at by trial and error. General sense is that if your sound source is very feeble, then you can reduce this distance. You can make it 3 centimeter, 6 centimeter, 9 centimeter, 12 centimeter. Take 7 8 readings. If your source output is very strong, then you can increase it, say 10 centimeter, 20 centimeter, 30 centimeter, so on and so forth. If you are playing it out through a speaker, then I don't know what distance you will have to keep. You will have to keep much larger distance if your speaker sound is very loud. So you have to keep the interval like 20, 40, 60, 80, so on and so forth. Use a scale to measure the distance from the source. Try to keep the direction of this distance perpendicular to the plane of the speaker. Okay, and used to that all throughout. We are not looking into the polar response of speaker, where we figure out in what direction how does it radiate. So we are not looking at that. We are looking only at one aspect, that how with the distance sound intensity drops. So keep your distance line perpendicular to the plane of the speaker. So having said that, uh, play the note from the source for 10 seconds. This is approximately, you can go up to 15, 20 seconds. Uh, Minimum 10 seconds you must play. Activate the sound sensor. I'm talking about Arduino Science Journal app. So it has multiple sensors. You have to activate the sound sensor and hit record button. So once you start the recording, then it will give you the reading. It will give you peak value, it will give you minimum value, it will give you the average value. So for 10 to 15 second average sound intensity from the app can be determined, and it can be noted down for the given distance. So let's see how does it work. This is my app. This is my sensors. Once I select, these are my type of sensor. I can select the dB sensor. Now you can see that it is giving the readings in dB. I can hit the record button here. The moment I will hit the record button, it will now start recording, and it will give me minimum, maximum and average. So I am more interested in the average value. Now, if your background noise is fluctuating, then the average may fluctuate slowly. So there could be like a traffic noise, horn noise, or anything in the background, somebody talk. All those will affect your average. So as I said, to begin with, see to it that you look for a quieter corner, quieter time, quieter place. Of course, everything is relative. And finally, you look at uh, if you gives, most of the background noises are momentary. They will appear for a very brief amount of time and disappear. So if you take 10 second, 15 second or 20-second average of your tone recorded, then most likely you will get an accurate reading. So don't worry much about it. This is, I have not shown you fully. In fact, you can record, the app records your recording. You can take snapshots and you can go to the gallery and many other things, and you can go back and check your data. So in fact, you don't even have to take you don't even have to start your decibel meter multiple times. In fact, one times, and you can do at different distances. So explore that. Now tabulate the average intensity in dB and distance in centimeter. That data I leave for you people to tabulate. How you will tabulate, you decide. You people are now in SYBSc. In fact, third semester, more than half of this course. So all these things you people should know, which is independent variable, which is dependent variable, where you want to place them in a table. So please figure it out. Add suitable columns for further calculations. I have already shown you or demonstrated you some of the mathematical calculation on the top. So whatever data you will get from the source, you need to modify it suitably further in order to reach to the graph. For that, you might need to add some more columns. So figure out and see what you want to do. Plot a suitable graph and find the value of n. So as I said, from the graph, value of n can be found. So please plot a suitable graph. What parameter on x-axis, what parameter on y-axis, how do you get your line, how do you get your n, etc. Please figure it out. I would recommend you that please do it first on with pen and pencil on the graph paper rather than doing it on the computer. So I will request you to give handwork a priority. Once you have done with handwork, and if you want to plot it on computer in some app, please you are free to do that. So results, eventually once you find n, then you can write your results as the intensity of sound drops as I is proportional to r power n. And then after that, I have some suggestions for you. If you are enthusiastic, you can try to mimic a free field. How would you mimic a free field? Just think about it. Remember, a free field has something which has no reflections. So your scenario, how do you make a free field? Think about it. I will give you a hint. If you are at some distance from the source, and if there are no hard surfaces surrounding it, then you can assume that the source is a free field. Just to give you an example, a speaker hanging on a railway platform for the announcement purpose, most of you must have seen it. If you are listening it from a distance, typically it acts like a free field. How would you create it at home? Think about it. You can repeat your experiment by using or by creating this kind of free field. You may repeat it for a softer surface like a thick towel or a carpet. So you can repeat your experiment. Remember, initially we did uh, with hard tiles at the bottom. If you have a carpet or a thick towel or something similar to that kind of background surface, then your readings will differ. Remember, this experiment is not going to take much time, so I strongly recommend you people to bring out these two modifications and then repeat it again, although I'm not making it compulsory. So please look into that. Okay, so that's right. So we have learnt. Let me very quickly, since it's an experimental part, let me very quickly go through it. So we talked about the point source, isotropic, 1 over r square law. Then we argued that how reflections from a surface one side may skew your 1 over r square law. And then we took a general law, I is proportional to r power n, and we aim to find that n value from our experiments. Our simple calculation, simple mathematical analysis tells us that if we plot, if we calculate sound in dB and distances in r, then a simple graph of this equation will give me the slope as 10 times n, and therefore n as slope divided by 10. And then we learnt how to perform this experiment, what app to use, why we are working at a particular frequency. I gave you some examples, what readings and how we have to take. Some examples over here we have seen, and how to go for the calculation. What are the results you will write, and what modifications you can bring to this experiment. So we can stop this online instructions and go back to Google Meet. Thank you.